This is chapter 2 in sapling, number 15. It says, rank the following 4 acids in order of increasing Bronsted acidity. So, what's it asking? So, Bronsted acidity. So the first thing you need to know before you even look at the molecules, if you don't know what Bronsted acidity means, it doesn't matter, right? So you got to look at do you know what it means to be a Bronsted acid? So, 2 things: acids are electron rich or electron deficient. Deficient. So acid means electron deficient. Got that down? A Bronsted acid means a particular type of acid. What kind of acid is a Bronsted acid? It's a hydrogen, right? It deals with H, right? So Bronsted acids give up hydrogens. Doesn't always have to be H+, it just gives up a hydrogen, right? So Bronsted acids break bonds to hydrogen, right? Usually the polar ones. The more polar, the better. All right, so now we know what Bronsted acid is. Let's actually look at the molecules. We have H2F+, we have CH3, 2OH, we have CH3, S, this is O, that's a plus there, my bad, SH2 plus, and we have just methanol, CH3OH. So whenever they do these rankings, right, they want us to rank. What I like to do, my strategy is I always like to find either the best or find the worst, and then fill in from there. Right? So, and the way to do that a lot of times is you got to figure out what do these things have in common, what do they not have in common. So what's one thing, which one doesn't look like the others? The which one? So if I know, I'll do A, B, C, and D. So which one doesn't look like the others? Why'd you say A?
It doesn't have carbon.
So it doesn't have carbon, that's right, but we're talking about acidity, right? We just did a definition of acidity. We just talked about acidity, it has to do with electron deficiency, right? So D, right? All these other ones have plus charges. This one doesn't have a plus charge, right? Just by necessary definition, acids are electron deficient. So, and what bond particular are we talking about here? And we're talking about the bonds to hydrogen, right? This HF bond, this OH bond, SH bond, or this OH bond. There's no plus charge here. I'm going to guess this is probably going to be the least acidic, right? So this would be, if I put this as number, so least acidic, right? Least acidic. Good. So now all of the ones that have left all have plus charges, right? So they're all pretty electron deficient. Now the question is, which bond is going to be the most reactive, the most acidic? So just for reference, right, we're talking about a HF bond here, right? If I draw these out in an expanded formula, right, if I draw these out that way. Now, why does that matter? Right, if you take a look here, right, we're asking ourselves, right, just our point of clarification, everybody realizes that right there is a carbon. That right there means a carbon. Right, it means it's bonded to 3 hydrogens. But do I draw the hydrogens in? No. Do I draw a carbon there? No. But that's a carbon. Just like over here, that's a carbon with 3 hydrogens. I didn't draw the hydrogens in, I did draw a carbon, that's a CH3 right there, right? So it might be helpful to see these in their expanded form. So right now we're looking at this, this, and this. All have plus charges. And we need to look at what bond? The bond to H, the bond to H, and the bond to H. So now, what's the difference?
The electronegativity.
But what's different in each molecule? What's different? Hydrogen's the same. They all have bonds of hydrogen, right? That's what we're talking about. Bronsted acids have to do with hydrogen bonds being broken. So what's different in all these? What is the hydrogen bind to? Is it a fluorine, an oxygen, or a sulfur? Then what do? I look at the periodic table and say, well, where are hydrogen, oxygen, and sulfur, or fluorine, oxygen, and sulfur? Where are they at in the periodic table, and how do they relate to each other? Right? So fluorine's the most electronegative. That's right. That's the top right. Oxygen is right to the left of fluorine, and sulfur is right below oxygen. So we gotta be careful here. This is gonna be a little tougher. Let's take a second and just think about this for a bit. All right, we're back. We've come to the consensus that since the fluorine is the most electronegative, this is probably the most polar covalent bond, the most reactive bond. So I'm gonna rank that one now, A here, as the most acidic. Fair enough? So what do we have left to do? Now we got to fill in the blanks. So now what we have left are these two. An oxygen with a plus charge or a sulfur with a plus charge? What's the difference between oxygen and sulfur? The size. So which one's going to have a more reactive bond to hydrogen? Which one's going to have less orbital overlap to hydrogen?
Oxygen.
Sulfur's bigger. Hydrogen's staying the same size.
Oh, less.
So what's going to have, which one? Sulfur will have less orbital overlap. Does that mean its bond is reactive or more reactive or less reactive? If you have less orbital overlap, you're more reactive because you're not sharing electrons very well. All right. Don't forget this. Don't forget our little. Remember, I'll draw a little picture here to remind ourselves.
Isn't oxygen more electronegative?
Oxygen is more electronegative, but as you go down the periodic table, that's not the thing that's important. Size is what's important. Size matters as well, right? You got to take size into account. So if here's an oxygen, right? It's bonded to hydrogen. Hydrogen's the same size. Here's a sulfur, right? There's a hydrogen, same size. You can clearly see, right? The sulfur and the hydrogen have less orbital overlap. That means that bond's more reactive, right? They're not sharing electrons as equally. So that means that bond is much weaker. So if we said, so if this was the most acidic, that's 1. This was 4, the least acidic. That means this would be 2, and then this would be 3. So let's go, this is chapter 2, number 17. Now for this one it says rank the given compounds based on the relative acidities. So again, relative acidities. And usually if they don't say anything, they usually mean a Bronsted acid. Right? If they just say relative acidity, so that's again just like the last problem we just did. So we're looking for H, and we're looking for electron deficiency, right? Our acids are, we have water, which isn't drawn out, right? Some of these aren't drawn out. We have acetylene. We have NH3. Oops, too much. NH3, we have an alkene. And then we also have methane, CH4. So again, let's take a look at these and say which one of these are not like the others. All right, or what do we have that's similar or not similar? So again, what bond are we looking at? Looking at bonds to hydrogen. There's an OH bond, a CH bond, an NH bond, a CH bond, and a CH bond. So again, we're trying to rank them. So let's do A, B, C, D, and E. So what do they have similar? What are they different? What's different about them? Let's just talk about it. So let's look at all the carbons. All this, there's 3 of them. B, D, and E are all CH.
The bonding.
What kind of bonding? So what's that called though? So they have different types of bonds. What's that called? What's the difference between those right now? Between B, D, and E, what's different about them? They all have CH bonds, but what about this carbon versus that carbon right there? What's different? So what's that called? You have the different types of the hybridization state, right? This carbon right here is what hybridization state? It has 2 pi bonds and a sigma bond and a sigma bond. It's sp hybridized. Box the hybridized state. Hopefully everybody recognizes that there's a carbon right here, even though we didn't write a C. There's just like there's a carbon here and here. So this carbon right here is what hybridization state? sp2. And this final last carbon, what's its hybridization state? sp3. It has no pi bonds. So that's sp3 hybridized. Generally speaking, what do you guys know about carbon-hydrogen bonds? Are they reactive or unreactive? A CH bond. Is that a polar covalent bond or a non-polar covalent bond? It's non-polar, right? Carbon-hydrogen bonds are really stable. So I'm not sure which one of these is the worst acid, is the least reactive acid, but one of them is. Right? Because what do you know about carbon-hydrogen bonds? Are they usually pretty unreactive, strong bonds? Yeah. So one of these is the worst.
Probably the single bond.
We'll get there. So the other two are OH and NH. So again, we have oxygen, nitrogen, and carbon. Those are the 3 ones we're comparing bond to hydrogen. So we look at our periodic table. Which one has the most polar bond to hydrogen? Oxygen, nitrogen, or carbon? Oxygen. Oxygen is the most electronegative. That means this bond is going to be the most polar, which means it's going to be the most reactive, which means it's going to be the most reactive acid. So we'll rank that one number 1, right? Again, the strategy of trying to box things in, right? This is the most acidic. We're not sure about the least acidic yet. That's tough. We know it's one of the carbon ones. We're not sure which. Which one's the next most acidic? If you just look at it, the NH3, right? The N-hydrogen bond, nitrogen-hydrogen bond, is more polar than any carbon-hydrogen bond. Well, it's close. So we'll guess that this is 2. We'll guess that this is 2, but I'm going to put a question mark there. I'll put a question mark there. All right. So logically speaking, we could say that. Again, I emphasize, you can look these numbers up, right? You wouldn't necessarily know, right? I told you, chemists are good at what? Are we good at predicting things? We're good after the fact and explaining things. We run the experiments and then we tell you why it worked or didn't work, right? So it's hard to predict without knowing or running the experiments. So I put a question mark next to this number 2. Question mark. Let's look at B, D, and E. So the difference is hybridization state. So for any reaction to take place, right, we're talking about reactions here, right, how reactive these things are. We need to break these CH bonds, that CH bond and one of these CH bonds. For a reaction to take place, one of 2 things must happen. Oops. Oh, I can't shrink it? No, it's just mad at me. Whoa. Well, let me shrink it. For a reaction to take place, one of 2 things must happen. Either you have reactive starting materials and or you have stable products. What do you guys know about this SPCH bond? Is it short or long? Short. Short bonds have more orbital overlap, right? So they're going to be reactive or less reactive? Less reactive. But here's the problem. Let's look at the conjugate bases for all of these. The actual product for all of these is what? So if this reacted, I would have a negative charge here. All right? If a base came and took that, H base. Right? Everybody agree with that? And that negative charge is represented by, right, there's lone pairs here. What molecular orbital are those lone pairs in? These lone pairs right there. What molecular orbital are they in? Well, let's take a step back. What are the molecular orbitals for this hybridized state? What are the hybrid orbitals for sp hybridized? What are the hybrid orbitals? I'll draw them in. What are they? Think about the bonds. What kind of bonds? What kind of bonds does this carbon have? Has 2 sigma bonds and 2 pi bonds. So if you have pi bonds, what kind of orbitals must you have? All right. So we know it has 2 p's. And what do we have left over then? You had an s and a p, and you mix those, right? What are the other 2 orbitals you end up with? The hybrid orbitals are? You end up with 2 sp orbitals, right? Don't forget our hybridized state and our hybrid orbitals. So I ask you again, where are these electrons? What molecular orbital those electrons end up in? What must they end up in? Did you break a pi bond? So where are these 2 electrons at? What molecular orbital are they in? What molecular orbitals do you have? These are the only 4 you have. You didn't break a pi bond, so it can't be the p's. So it's in an sp orbital, right? These electrons are in an sp orbital. Think about it this way. What was forming this bond? What molecular orbital was forming this bond? An s for the hydrogen, and then on the carbon, what molecular orbital was it? sp. Right, you got to go back and review that. Right. Keep on flying on you. Right? This carbon is sp hybridized. What kind of bonds does it have? It has 2 pi bonds and 2 sigmas. If you have a pi bond, for every pi bond you have to have a p orbital, p and a p. Whatever's left over, you mix to make sigma bonds. This carbon was using an sp orbital to form this bond to hydrogen. It was also using an sp orbital to form a sigma bond to this carbon. When this bond broke, these 2 electrons, all right, let me even draw it out. When base came in, it attacked right there, the 2 electrons in this bond went back into that orbital. And that's where they ended up, in an sp orbital by themselves. Do you see that? Okay. Fine and good. We'll come back to that in a second. So it's in an sp orbital. What do you guys remember about, actually no, let's do it right now. What do you guys remember about an sp orbital? What's its shape like? It has 2 parts. That's the geometry. What's the shape of an sp orbital? Half p, half s. So it's me right now. It's a little more round than it used to be. Right? So maybe it looks like that. Right? A little fatter. That's an sp orbital. That's what an sp orbital looks like. That's going to become important. Because if I put electrons in there, it's going to maybe make it more or less stable. We'll see. Think about that. What about an sp2 orbital? If I broke this bond right here, and I drew the product, what molecular orbital are these lone pairs going to be in now? In an sp2 orbital. Right? Because what are the hybrid orbitals for? What are the hybrid orbitals for an sp hybridized carbon? What are they? You have how many pi bonds to this carbon? 1. So you must have at least 1 p orbital. P orbitals form pi bonds. So what do you have left over? 2 p's and an s, and you take them all and you mix up those, and you end up with 3 sp2s. Right? Those form the sigma bonds. Right? Everybody see this carbon has a pi bond, a sigma, and another sigma? So the lone pairs are in an sp2 orbital. Ready to do the last one? So the last one, where are the electrons going to go now? You're going to have a carbon with H's, And where is that lone pair going to be? What molecular orbital is that lone pair going to be in? sp3. Perfect. Let's draw the shape for an sp3. What's the sp3 shape look like? So it's 3 parts, or 4 parts. 3 parts P, 1 part S. So it's long and skinny. 20-year-old me. Right? So there's the sp3. And then what does the sp2 look like?
Wouldn't that be sp2 since it's only bonding to the atoms?
Nope. Your Gen Chem books talk about bonding to atoms. It drives me crazy. Nope. Think about what bonds it has. Not bonding sites. I don't know what it says. Things you're bonded to. Nonsense.
So the lone pairs count as a bond in a way?
Now, we talked about this already. A carbanion wants to be sp3 hybridized. Why? Because it gets the electrons all away from each other as much as possible, right?
So that would be sp3.
That is sp3. It would be and is. Good. What's an sp2 orbital look like relative to these? It'd be somewhere in between. I'm not a good drawer, but there it is. So there's an sp2. This was an sp3. Which one of these do you think is happier having the lone pair in it? sp, sp2, or sp3? Which one's happier with the negative charge in it?
sp3,
Why?
because it's further away
From what?
from the nucleus, or from
Whoa. You said it. They're further away from the nucleus. But wait a second. What's in the nucleus?
positive charge,
And what are you said? What are electrons?
negative,
And the first commandment of organic chemistry is? So which orbital would you rather have the lone pair in? sp3 makes it as far away as possible. Where's the nucleus? Nucleus is right here. Nucleus is right here. You want the lone pair in an sp orbital. Because that's as close, that's fat. That's close to the nucleus. Opposites attract. Opposites attract. Right? Where's the orbital at? Where's the space? So the difference here is, here's the tricky part. So this is actually our second best acid. This is not. This is actually number 3. Then this is 4, and this is 5. You wouldn't know that off the top of your head. You'd have to look up the pKa values. But I could tell you this answer, and you could explain why. So what's going on here? So there's 2 factors. There's obviously electronegativity matters, right? If we're comparing carbon to nitrogen to oxygen, the electronegativity changes. Right? So that's one factor that affects acidity, is electronegativity. But what else, according to this, what I just did here, what else affects electronegativity? Hybridization does. And sometimes hybridization is more important, but I can't tell you it always is. I'm not going to tell you that. In this case it is. But you wouldn't necessarily have known that until you ran the experiment. But now that you know this, you should be able to explain it. So how are we going to explain this? So I can explain this bond being the most reactive because this is the most polar bond, right? Now this one's a little trickier. Why do you what do you think this means? The fact that this is more acidic, that this bond is more reactive. Is it really more reactive? Is that bond really more reactive? For a reaction to take place, one of 2 things must be going on. You have reactive starting materials and or stable products. So what does that tell you about the stability of this product? And why is it stable? Because the electrons are close to the nucleus. So just because you have a really stable starting material, does that mean your reaction is never going to take place? No. Because you can form really stable products, right? You could have a really right? You could have that delta, delta H, delta G, one of those things, right? So it's not just about how reactive the starting materials is, it's also about how stable the products can be. So it turns out putting a lone pair in sp2 or sp3 orbitals, real bad. Those guys are super reactive. As in, these are not acidic at all, right? So this is better, but this is the worst. And then nitrogen comes in at the end. Nitrogen is still better than these guys, but it's not great. Does that help? This is tough. This is tough because you're gonna have 5 different factors, right? There's all sorts of things that are gonna affect acidity, and I'm not going to tell you one's more important than the other. But it is, the difference is, right, seeing what's going on here, right? You look at these, you say, I have oxygen, carbon, and nitrogen. I look at the periodic table, that's an electronegativity difference. But then I also see an sp2 and sp3 hybridized carbon. That's a hybridization difference, right? How does that affect acidity? Understand those factors and how they interplay. So the tough part about this problem is you're trying to compare two factors and you don't know which one's more important, right? What are the two factors we're comparing? We're comparing electronegativity, right? Carbon and nitrogen and oxygen. But we're also comparing hybridization. And you wouldn't necessarily know which one's more important, right? You'd have to run the experiment. You'd have to have the pKa values. Right, so if I were to give you a question like this on a test or a quiz, I would probably give you these and then tell you, I would give you the ranking. I would say these acids are ranked from most acidic to least acidic. Why? You could do that. Right, this is a problem that's similar to number 1 in chapter 2. Not exactly the same. So the question, chapter 2, is asking, essentially, they're showing you an organic acid, and they want you to draw its Lewis structure with all bonds, unshared electron pairs, and minimize formal charges where you can. So I'm going to show you, this is the molecular formula I'm going to give you, is HSO3 CH3. So see if you can draw the Lewis dot structure for that. So, all right, so working on this, remember sulfur is in the second row of the periodic table, so it can expand its octet, doesn't have to follow the octet rule. Also, way to do these, usually you draw the sulfur in the middle. And usually you don't want hydrogen bonded to the sulfur. So I usually do this one, I would say oxygen wants to be bound like this. Usually try to make an OH. And I put the CH3 over here. So that would be this methane sulfur compound. Right? Usually if you see sulfur with O3 or O4, you're in for this double bonded thing. Right? And then usually the hydrogen wants to be on the oxygens if it can. Not necessarily the sulfur, rather be on the oxygens. Okay. We're still not done yet, though, because sapling says all bonds, got that done. Right? Let me draw this a little cleaner. It's not going to let me know.
Is that from enough valence electrons in that structure?
Yep, I think so. No, well, it depends. So elements themselves can be electron rich or electron deficient, right? Certain parts of our electron rich or certain parts are electron deficient. The next part, right, so we have the bonds all drawn in, but this is the classic sapling type deal. They want you to draw in all your unshared electron pairs. So does carbon have any unshared electron pairs? No. Does sulfur? No. But the oxygens do. Good. And wants us to minimize the formal charges. I don't see any formal charges. Is everybody okay? Oxygen has 2 bonds. It wants 2 bonds. Sulfur has 6, but that's cool. Carbon has 4. Everybody's happy, right? There's no charges here.
Can you explain why sulfur's okay with that?
Sulfur's okay with that because it's in the third row of the periodic table, so it gets bigger. So because it's lower, it can have an expanded octet. It's okay with having more electrons around it because it's bigger.
So anything on the second row cannot have more than
The second row, we're sticking with 8. We want 8. All right? Second row, we pretty much want 8. I like to stay there with that. So the next part says, that's the first part, it says draw a complete Lewis structure for the conjugate acid of this. So where is the conjugate acid of this? So you're going to add H plus to this. So I'm going to put in plus H plus. Now the question is, where is this most electron rich and why? This actually comes back to that problem we just did. The sulfur is electron rich? So if this is the acid, what is this going to have to be? The base. But we can't just call this whole thing the base. You got to tell me exactly where it's basic. Where is it most electron rich? Which oxygen? it matters.
No.
Let's look-
Without the double bond?
Let's take a question. Let's take a step back. These oxygens, so these oxygens, this oxygen and this oxygen are pretty much the same, right? These two are different. What's different about them?
They're hybridization.
Their hybridization state. Ooh. This is what hybridization state? sp2 hybridized state. This oxygen is what hybridized state? sp3. Very good. Remember we boxed in the hybridized states. If I circled this one lone pair right here, what hybrid orbital is that lone pair in? It's in an sp3 orbital. Very good. Let's draw an sp3 orbital. And we'll put the lone pair is really all parts of it, right? That's an sp3 orbital. All right? sp3. What about this lone pair? What hybrid orbital is that lone pair in? It's in an sp2. Very good. What does an sp2 look like relative to an sp3? A little shorter and a little fatter. It's not as fat as an sp, but it's getting there. sp2. So which lone pair do you think is going to be more reactive? A lone pair in an sp2 or a lone pair in an sp3? Why sp2?
Because they're more attraction.
So we want the lone pair to be more reactive, right? So if we want the lone pair to be more reactive, do we want it close to the nucleus or far away from the nucleus? If it's close to the nucleus ain't letting go, baby. If it's close to the nucleus is thanks. You're mine. If you're farther away from the nucleus, you're more reactive. Which one of these is going to make it so the lone pair is farther away from the nucleus? The sp3. So it's actually going to be this lone pair that takes it. So what's the conjugate acid going to look like? It's going to look like this. Drawing our lone pairs. One of the lone pairs got sucked up in there, so there's only one left. And I need to balance my charge. Where should there be a plus charge? Hopefully on this oxygen, right, which now has 3 bonds when it had 2 before. So this is the conjugate acid of this. Again. So don't confuse what we did before. Now we're looking at this as a base. So now we want the lone pairs to be reactive. We don't want the lone pairs close to the nucleus. Now we want them to be reactive. This is the base now. And it's reacting with the acid. Before this, we were looking at it as an acid and wanted a stable product or stable conjugate base. So we want the lone pairs close. If you want something stable, right, you put the lone pairs close to the nucleus. If you want them reactive, you get them away. This problem is similar to something in the book, like number 16 in chapter 2. It's not just like that. But if I took, let's say, I took this, and I'm going to react it with, oh, I don't want to do that. That's a little too similar. I react it with this, presumably smelly compound. The way we talk about reactions, we talk about mechanisms. So a mechanism is how reactions take place. Essentially how electrons move, right? I told you guys, all reactions in organic chemistry, all reactions in the world, somebody has electrons, somebody wants electrons. Electrons are the superstars of organic chemistry. It's where all the action takes place. So we have to signify how electrons move, how electrons flow, and that's called a mechanism. So the way we do that, and part of the reason is I like to draw in lone pairs always. Because really, right, when we make a bond, how many electrons are in a bond? 2. So this is a way for us to see those electrons move and understand what new bonds are formed and what bonds are broken. Also, when we first did Lewis dot structures, I had you write in, remember, we talked about writing in the dots on the bonds to signify there's 2 electrons there. This becomes important to help us keep track of electrons now, right? So sulfur also has 2 lone pairs as well. Sometimes it's just good practice to draw in all the lone pairs, even if I don't do it for you. Right? That's the other thing. When you do sampling, you should do it on a piece of paper first. Don't try to do it on the computer the whole time. Somebody remind me to tell people that tomorrow. Everyone listening, make sure you do it on a piece of paper. It's better that way. And then put it on the computer. But the way mechanisms work is we're going to talk about how electrons flow. So electrons or arrows, we call these arrows, always start at electron density. So in this case, we have 2 things. We have A and we have B. Which one's more electron rich, A or B? A, why?
It has 7 and 6 grams.
Even simpler than that.
That's negative
It's
charge.
got a negative charge. It's got a negative charge. That's probably going to be where my arrows start. Now, where exactly do my arrows start at? You can't just say, right? You can't just, so when you draw arrows, you can't just willy-nilly say it starts from someplace, right? You got to point out exactly where it starts. So where is it actually electron dense at? What specific part of that molecule? On the outer ones, but what do you mean outer ones? You mean the lone pairs, right? So now I've started my arrow. I'm going to stop, right? So I've identified where it's most electron rich. You see how I lassoed those electrons? They're coming with me. I'm taking them with me. I'm going to form a new bond. How many electrons in a bond? Those 2 electrons are going to form a new bond. I'm taking them with me to form a new bond. What's the most delta plus spot in this molecule? Where's it most electron deficient? What's the most polar bond? Look at the periodic table. What's my most polar bond? Sulfur and hydrogen, right? This is my most polar bond. Where is it delta plus at? The sulfur or the hydrogen? Look at electronegativity. Who's more electronegative? Sulfur or hydrogen? Sulfur is. So my electrons are going to go where? They're going to attack the most delta plus spot, right? Because the first commandment of organic chemistry is opposites attract. Here's a bunch of electrons. They're going to go for somebody that doesn't have a bunch of electrons. That's delta plus. Right? So here we go. It's going to attack. If I make a new bond, what must I do? I must break a bond. So these 2 electrons are going to go where? To that sulfur. It's an acid-base reaction, so it's equilibrium arrows. So what's the product of this reaction? I have to balance my charge. On the right-hand side here, what's my overall charge? Overall charge is what? Negative, right? I have a -1 overall charge. So over here I must have what? An overall negative charge, hopefully. Yes. Got to balance my charges. What new bond did I form? An OH bond, right? So I have a new OH bond. I still have the lone pairs. What bond did I break? SH bond. So the sulfur got what out of this deal? Another lone pair, right? See the lone pair it got? See the lone pair the sulfur got right there? So I have to balance my charge. Where's the negative charge at? Sulfur, absolutely. So I have to balance my charge, right? I started off with a negative charge over here, overall. So overall here on the other side of the reaction, I better have a negative charge too. And if you look at it, this oxygen's giving up electrons, right? See the electrons leaving the oxygen? See the sulfur getting 2 electrons? So the oxygen no longer has a minus charge, but the sulfur got electrons, so it has a negative charge. Take it a step further. Let's talk about this equilibrium arrows right here. Which way does it really lie? And how would we tell that? Are we going to favor starting materials or are we going to favor products in this case? What do you think? What's the differences? We're overall minus charge on both sides. What's the difference? Sure, you can think of it that way. You can think of it, so which one's going to, when you say dissociate, what bond are you talking about? So you're talking about the OH bond versus an SH bond. Which bond is a more reactive bond, an SH or an OH bond? What's the difference between oxygen and sulfur? Sulfur's bigger, so that's going to be this is going to be a more reactive bond. So you predict it favored this, right? Because this bond is more reactive. That's one reason. That's a good one. Somebody give me another reason. So you looked at how acidic they were. Perfectly awesome. What else could you look at? So you compared the acids to each other. What else could you compare? Compare the bases. Who's happier with a negative charge? Oxygen or sulfur? Who's bigger? Sulfur. Who could slosh the electrons around better? Sulfur. Right? So it works, right? Either argument, it's the same argument. Right? This is a more reactive bond. That means these are more likely. This is a more stable product because sulfur is bigger and can slosh on the electrons more. That's also a reason why this would go. Right? Every reaction that takes place, one of two things. Either you have reactive starting materials and or, it could be both or one or the other, you form really stable products. In this case, it's both. We have already seen one case where it was just one.